So, what we did still yesterday, I'm doing just a quick recap, is okay, we are looking for another technique that avoids computing the optimal step size and still makes the whole algorithm work in some way. So what we did, we take this function here and we compute the derivative of this function phi at 0. So this function phi is approximately equal for small s to a line that we call ls, which is phi 0 plus s delta k, where delta k is this delta k here, this one here. So this delta k is negative. Okay, so this is a line with negative slope. And also we introduce some parameter alpha, which only has to belong to the interval 0, 1. And so together with this L line, we define another line that I call L bar of S, which is essentially, it's more or less the same thing, but instead of having slope delta k, it has a slope which is alpha delta k. And we did a little picture yesterday. If this is S, so somewhere here we have our function phi of S. Here is S equal to 0. We compute the tangent line. So that's the tangent line L of S. And the tilted line L bar is something like this. So this is L bar of S. And the reason we do this is that this line L bar defines like what we consider a sufficient rate of decrease of our function phi of S. And since this line will at some point, or maybe even in more than one point, if this function does like this, okay, in several points may cross the actual function phi of S, we say that we are happy with all those points where the function phi of S is below this line L bar. And in particular, we can define the smallest of such points, which in this plot here is this S bar here. And of course, for all values of S that are below S bar, we have this condition is satisfied, so the function phi is below this line L bar. And so this is what we call the Armijou condition. Okay, this is maybe a nicer plot, but it is essentially the same thing here. Line LS, line L bar, this is phi, this is S bar. And these are actually the bold lines, the parts, the values of S that do satisfy the Armijou condition. Of course, this plot is for a function f0 that it is not necessarily convex. Okay? Otherwise, if f0 is convex, of course, it is convex along any line, so also phi will be convex. So in the convex case, we will not have this kind of oscillation here. Phi of S will be also convex. But for the time being, we do not need to enforce convexity. We will do so later. Okay, so the problem with this Armijou condition alone is that okay, we find a value S bar. It exists a value S bar such that for all S smaller than S bar, we have a sufficient rate of decrease, but this is a rate of decrease still this is not enough for avoiding choosing a step size which is too small. Okay, so we don't want the step size to be too small for almost evident reasons, because if this is the algorithm essentially, right? So if the step size is very, very small, we proceed very slowly to the optimum, or maybe we may not even converge if S is not guaranteed to be large enough. So we have actually two problems. The step size has to be less than or equal to S bar in order to satisfy the Armigio condition, but the step size also should not be too small. Okay. So how do we avoid choosing too small step size? Well, we do this. We apply this procedure that is called backtracking, which is essentially a kind of sort of bisection or something similar to bisection. So it means that we start essentially from some S bar, for some initial value of the step size that I call S initial. For instance, 1, like 1 means doing a full step size. So maybe this initial step size does not satisfy the Armigio condition. And so if it does not satisfy the Armigio condition, we progressively reduce it and check the Armigio condition. Reduce and check, reduce and check. So this is expressed in this procedure here. So beta here is the rate of decrease of our step size. So we start with an initial step size, which is some positive constant, typically 1. Okay, delta K is this delta K here. So we check the Armigio condition. So we check if the value of the function, this is phi actually, okay, so this is phi of S. We check if phi of our current S is below line L bar for our current point. If yes, if it is below, then Armigio condition is satisfied, and we get away with our current S. If it is not, like if we are here, then we just multiply S by beta. So beta is less than 1, so we decrease, and we iterate. Okay? So this simple idea guarantees that since an S bar exists, at some point we will stop. So we will find for sure a suitable step size satisfying the Armigio condition. And on the other hand, it also guarantees that we do not go too far. As soon as we are to the left of S bar, then we stop. Okay, so we don't get too close to 0.
It's clear for one dimension case.
It is always in one dimension, because here S is a single variable, because it is the restriction of the function along a line. So it is always one dimensional. So S is a scalar. Okay? It's a sort of approximate line search. So now, all these holds in general for directions Vk that only satisfy this condition, so that are descent direction. Now I specify what happens if we take like the steepest descent direction, means Vk is the anti-gradient, so it's minus the gradient, okay? So from now on we understand that the direction Vk is minus the gradient, and we saw yesterday that this is the direction that gives the highest rate of decrease locally. Okay? So it happens that if we just reason in this full generality, taking the gradient, not much actually can be said about the convergence of this algorithm. So if we are not assuming convexity, we are not assuming anything except existence of the gradient, so the fact that the function is differential. Well, under this very general setup, we cannot say much about the convergence of this algorithm. Okay? It does something, it tries to minimize, to decrease the function at each step, but that's about all we can say. So we need to put some more assumptions now if we want to prove something. So, this brings us back to all those technical preliminaries that I introduced yesterday morning. In particular, we need this assumption of Lipschitz continuity of the gradient. Okay, so we'll assume from now on that the function has Lipschitz continuous gradient. So still, we're not even requiring convexity, okay? Not convex, but the gradient is Lipschitz continuous. So it means that there exists a constant, a positive constant L, such that this Lipschitz condition on the gradient holds. Okay, so we will say we're again on this idea of the step size. We will see that indeed, if the gradient satisfies that Lipschitz condition, this will guarantee that the step size will not be too small, because indeed we know that there exists an S bar always. Okay, but this S bar again, it can be very close to zero, or too close to zero. So let's see what we can say about S bar under the Lipschitz condition on the gradient. Okay, you might remember from yesterday that if the function has Lipschitz continuous gradient, then we can find a quadratic function that we call f up, that overbounds our function f0. So this is an immediate consequence. As soon as you have Lipschitz gradient, then you can construct this quadratic function that stays above our function. So now let us consider the restriction of both our objective and its upper bound along the direction, along the line that we are working with, this line here. So the restriction of f0 along this line, we called it phi of s, this one here. And the restriction of the upper bound along this line, I call it phi up of s. And of course, phi up of s is above phi s, okay? Because f up is above f0, and it's above f0 along any line. Moreover, if you look at this expression, phi s and phi up have the same tangent line at s equal to 0, which is this ls. So here you can see we have phi of s, and we have another function here, which is a quadratic function, and which is phi up of s, okay? And phi up is above phi of s everywhere. And at 0, phi up and phi have the same tangent line, L of s. Alright? Then the idea is that the line that we defined before, L bar, will cross both phi and phi. And actually, it will cross phi before S bar, for sure. So the point, and by doing a little calculation, which is quite simple in this specific case, the point at which the line L bar crosses phi up is some point here that that we call S up. Okay? And the key idea here is that S up can be computed, and it is related to the Lipschitz constant. So S up is 2 over L 1 minus alpha. This point here. So this is very important because we have now an explicit value of the step size, S up bar, that has the property that since S up bar is on the left to S bar, always. Basically, well, first of all, we may choose just S up bar constant. Always the same step size will satisfy the Armija condition. So this step size here satisfies the Armija condition, right? So one possibility is, well, just forget about this line search, backtracking, and take always at each step a constant step size given by S bar up, and this satisfies the Armija condition. Okay, so this of course it can be done, but it can be done only if you really know the constant, the Lipschitz constant L. So one thing is saying that the gradient is Lipschitz continuous, so there exists an L, okay? And another thing is to say that there exists an L and I know the value of L, okay? That's two different things. So usually we may make this assumption of Lipschitz continuity, but we do not actually know the value of L. So the drawback of using this constant step size here is that we, and sometimes we do not know the actual value of L. In this case, we just, if we don't know exactly this value, but we know that there exists a value here which is on the left of L bar, then we can just use backtracking as we explained before. So this is again the same kind of picture. The line, the tangent line at 0 of phi and of phi up, and this is our S bar up, which is the point where L bar crosses the overbounding function here. So again, suppose that we initialize the backtracking procedure with some initial step size. Then either this initial value satisfies the Armija condition, and then we are done, or this is iteratively reduced until it does. But the point is that the iterative reduction certainly stops at a value which is, well, let's say the minimum between the initial step size and beta times S bar up. This just means that either I stop at the initial step size, let's say equal to 1, or I go, and for sure, as soon as I go to the left of S up bar, then I will stop because I am satisfying for sure the Armija condition. So Sk now is lower bounded by some number, okay? So it cannot be smaller than some quantity which is here, and this avoids going in this region to close to 0. So this I call S lower bound, this number, okay? So the important point is that if there exists some Lipschitz constant L, there also exists a lower bound SLB, which is explicitly given by this formula, and S bar up depends on the Lipschitz constant. But what we know is that the step sizes will be always no smaller than S lower bound. Okay? So there is a value here, S lower bound. And all step sizes that we obtain with our iterative backtracking technique will always be larger than this quantity, always. Okay. So now we consider the gradient algorithm. So the gradient algorithm is just this algorithm here, where Vk is minus the gradient. Okay? And so if you put Vk equal to minus the gradient here, well, this becomes the iteration, and we assume that we are running these iterations in such a way that at each step we compute the step size according to this Armijo, to this backtracking technique. Therefore, we have this. This is the main point. So if we are using the Armijo technique, the backtracking technique, sorry, what we know is that the value of the objective at the new point, due to this thing here, the value of the function of the new point will be less than or equal to the value at the initial point minus sk alpha times the norm of the gradient. Okay? The norm of the gradient is nothing but the norm of the gradient squared is delta, is what we called before delta. Because if v is minus the gradient, delta is, well, minus the norm of the gradient squared, okay? Alright. So we have this, that the difference of the value of the objective from one step to the next, okay, is greater than or equal to this quantity, where this is the step size. Okay? And since the step size, here you see this is a critical passage, critical point, the step size is always larger than the lower bound on the step size. So this is greater than or equal to S lower bound alpha norm of the gradient. Alright? So if you can see that this is a key inequality because it gives a minimum decrease from one step to the next of our function. If you turn this around, it tells you that f0 at the new point is smaller than f0 at the old point minus this quantity. Okay? So we decrease it by this amount here at least. So this quantity here is the decrease that we get of our objective functions at each step. Now, so the step is, the iteration is k. We can sum this, the left side and the right side of these two inequality, of this inequality here, over the iterations from the initial one to running k. So if we sum all this, we get S lower bound alpha, the summation of these norms of gradient. Then this has to be less than or equal to the summation over k of all this. But you can see that if you sum over k, there is always one of the two terms that cancels out. And so overall, this sum is just equal to f0 at the initial point minus f0 at the k plus 1 point. Right? Because if you sum it here, there is one term that cancels out in all this sum. And so only the initial one and the final one remain. But then, the value of the function at any point, so also at the k plus 1 point, will always be larger than the optimal value of the function, by definition, because this is the optimum. So this difference here is less than or equal to this difference. So you see now that the difference, this is the gap of optimality between the initial point and the optimal value is larger than this sum. But now, this quantity here depends only on the initial point, and it is a bounded quantity, it's a finite quantity, it's a number, okay? This is a number that only depends on the initial point. Given the initial point, we have a number here, okay? So it's a fixed number. So now it means that if we let k go to infinity, so we now take an infinite summation, we have that this limit here of this summation remains bounded by a constant. Okay? So this summation remains bounded when k goes to infinity. And the only way that that summation may remain bounded when you sum an infinite number of terms is that the limit over k of the summands has to tend to 0. Okay? So this is actually a first result that we get from the gradient algorithm with no convexity requirement, just Lipschitz continuity of the gradient. And what is the result? Is that the gradient algorithm has this property. If it runs indefinitely, it converges to some point such that the gradient tends to 0. So the sequence of gradients go to 0. Or in other words, it converges to a so-called stationary point of our objective function. A stationary point is a point of f0 where the gradient is 0. So the points where the gradient is 0 are called stationary points. What are stationary points? Well, of course, stationary points can be minima, can be maxima, can be inflection points or saddle points of a function in general. Okay? If there is no convexity requirement, this doesn't mean that we converge to a minimum. Okay? It only means that we converge to a stationary point. And that's all we can say in this kind of generality. Well, not all. We can say something else. We can notice that, okay, we have this summation of the gradient squared. The summation, of course, is greater than or equal to k plus 1 because there are k plus 1 terms. And instead of this, we sum the minimum of these quantities. Of course, the summation of some quantities is greater than or equal k plus 1 times the minimum of those quantities. And therefore, we can conclude, we can find this kind of inequality is that if we define gk star as the minimum gradient, so during our iteration, let's say that we record the minimum from 0 to k of the gradients seen so far, and the minimum gradient is less than or equal to this complicated expression here, but well, this is a constant. This is also some constant that depends only on the initial condition of the problem, and the important part is this one here. It means that the minimum gradient goes to 0 as 1 over the square root of the iteration number. Okay? This is considered like a slow convergence. So 1 over the square root of the iteration number is the rate at which the minimal gradient goes to 0. This also gives us a useful so-called stopping criterion for our algorithm, because since here the purpose is to find a stationary point, so a point where the gradient is 0, we will never actually get a stationary point because this is achieved at infinity, but essentially we fix some epsilon, which is our tolerance, and when the gradient, the norm of the gradient is below this tolerance, we say, okay, we are almost at the stationary point, up to accuracy or precision epsilon, where maybe you take epsilon equal to 10 to the minus 8 or 10 to the minus 6, and so when we reach this, you exit, and this is something you can check in the course of execution of your algorithm, and if you just turn around that previous bound that I showed, it also gives you like a figure of the complexity, if you like, or the number of iterations that are required by this algorithm to reach the precision that you want. And so there are several things in here. This is again something that depends on the initial conditions. This depends, in this lower bound there are some hidden constants, and in particular the Lipschitz constant is hidden in here. But well, even if you don't know exactly the value of the constant, you know that this is a constant. And so what counts is against the rate, so you need a number of iterations that grow as 1 over epsilon squared. Okay, so which can be quite big. If we take epsilon 10 to the minus 6, it means that we need, 10 to the 12 iteration. So this is not a very nice theoretical rate of convergence, but it is like kind of worst case convergence. Okay, so if there are no further questions on this, let's now see what happens if we now add to the picture the hypothesis of convexity. Okay? So now we consider not general F0 but convex F0. So as soon as F0 is convex, of course also phi becomes convex because phi is just the restriction of F0 along the line. And also another thing becomes immediate without any further reasoning, and that the algorithm for sure now converges to a global minimum. Why? Well, because for a convex function, this condition that the gradient is 0 is necessary and sufficient for a point to be a global minimum. So now, already without any further analysis, for convex function, we converge to a global minimum, not only to a stationary point. Okay? Because actually, simply because all stationary points are global minima for convex functions. But we can see actually, we can obtain something more also on the, let's say, speed of convergence of the method for convex functions. Okay, so here, for my convenience and simplicity, I fix the backtracking parameter alpha to 1 over 2. This is not critical. And so if we fix it at 1 over 2, this is the condition, the Armigio condition at each step of the gradient method. We have already seen it. But you see now, since F0 is convex, we may remember the first equation that I showed yesterday morning. So the fundamental in a convex differentiable function is that the function is lower bounded by the tangent hyperplane to the graph at point x. So since here convexity comes into the picture and establishes this inequality. If we now take this inequality, and this also for every y, so it will hold also for the optimal point that we are seeking. So if I plug in place of y, I plug x star, then this inequality becomes this inequality. I just put f0 x on the left, f0 y on the right, and f0 y computed at x star is f0 star. So we have this this relation that holds for the optimal that relation. Okay, so now this is a nasty slide here, but not so difficult to understand. So we substitute now this condition into this one here, and what we get is this. So we can say that f0 at the new point of the algorithm is less than or equal to this. Okay, so this is just is given by the Armija condition. Okay, this is true just for the Armija condition. That we put alpha equal to 1/2, right? And we use that other condition that is on the previous slide, and so we have this thing here that holds. And now there is a series of very boring tricks that I don't really want to explain here, but they are written here on the slide. So if you are very careful, you can just check, you can back check that you can go from here to here and these two things are equal. Well, you just express this norm squared as the inner product of xk minus x star transpose times itself. And then you do some further manipulation. Then at a certain point you use the fact that by this backtracking that we are using, the step size are always larger than or equal to some lower bound. And then we finally get to this expression here, which is still not very revealing at this point. Okay. I find myself quite incredible that it is so complicated to analyze such a simple. I think that the simplest algorithm that we know for optimization is the gradient algorithm. It's already a mess. Anyway, so let's consider this inequality here. From here, after all this chain, we get here. So now, let's write this inequality for all k, 0, 1, 2, 3, 4. So let's take k equal to 0. So for k equal to 0, this is f0 of x1. This is always f0 star. So we'll put it on the left here. And in this part, we have 1/2 as lower bound, and here k equal to 0, k plus 1 equal to 1. So this is the first inequality for k equal to 0. Then we write the same inequality for k equal to 1, and we get this, and for k equal to 2, and we get this, and we go on like this for all k. And then, as more or less as we did before, we sum all these over k. From 1 to k, we sum all of those differences, and once again, there are terms that cancel out in this summation, and what we end up with is saying that this summation remains upper bounded by this quantity. Okay? Now, the sequence here is non-increasing with respect to k. Why? Well, we have seen before that at each step of the gradient algorithm, we decrease a little bit our function. Okay, so f0 with iteration k, f0 decreases. Okay, always decreases, or at least it does not increase. Okay. So f0 xk minus f star is non-increasing with respect to k. And therefore, if we have a non-increasing sequence, the value of this quantity here is no larger than the average of the previous values of the sequence. At any point we are, the value at this point is no larger than the values of the previous points, than the average of the previous points. So the value, this values is no larger than 1 over k, the summation of the previous ones. Okay? Including myself, k. And this summation, we take it from here, is bounded by 1 over s lower bound, k, and this thing here. Okay? So if we look at this now, we get something interesting because you see this quantity here is again some fixed number which depends only on the initial condition. So I give to the algorithm my initial x0, and then I have some number which is the distance of the initial condition from the optimal point, which by the way I don't know what that is, but it's a number. Okay? What counts here is this 1 over k that gives the rate. So this equation says that my objective value converges to the optimal objective value at a rate 1 over k. Okay? Which is better than what we had before, who was 1 over square root of k.
But square root of k we have for gradient. But
Yes, for gradient. For gradient.
and it is the same if the
Yeah.
Function function is.
Yeah. Right. Correct. Thank you. But in that case, in the previous case, that was all we could say about, because we didn't have convex. Alright, so now it goes to this as 1 over k. Or we can invert this, this relation here, and if we like, we can express explicitly like the maximum number of iterations that we need in order to reach some precision epsilon prime here on the objective value, and it's something that goes as 1 over epsilon. Okay? Okay, so this is what we can say about this method for convex functions. What about strongly convex functions? So here we are putting some more structure. So now we consider functions that are not only convex, but that are strongly convex. So if we go back to the slides from yesterday, you may remember that if a function is strongly convex, then its Hessian is upper and lower bounded by two constants, the norm of the Hessians, and actually a strongly convex function can be so lower bounded by a quadratic function and upper bounded by a quadratic function. So here is again the iteration satisfying the Armijo condition. Okay, these are quite obvious steps. So we take this basic inequality here that comes from the Armijo condition, and we subtract f0 on both sides. So this becomes f0 plus 1 minus f0 star, and here we have this quantity here. And now what we do is we use this bound derived in 12, which I don't remember even what is 12 now. Let's go and see what is 12, if we like to. So what is 12? It's this equation here that comes from the lower bounding, the quadratic lower bounding of the function that say that f0 star is greater than or equal to f0 minus 1 over 2m. This m is the strong convexity constant of the function. So we are here, I guess. Okay. So we have this. elaborate on this. These are passages that you can follow from the slides, and so we conclude that this kind of relation has to hold. So f0 at some iteration minus f0 star is equal to 1 minus m as lower bound, and this quantity, which is just the gap, the optimality gap at the previous step. Now again, okay, there is some relation that holds due to the way we construct this S lower bound, which is related to the Lipschitz constant, which in the case of strongly convex function, instead of calling it L, it's this capital M, that's the Lipschitz constant on the gradient. Well, so to make things short, what we have is this, is that the optimality gap at one iteration is less than or equal to some constant times the previous optimality gap. And the key point of all this playing with constants here is that this constant is smaller than 1. Okay? It is smaller than 1. So since it is smaller than 1, here it's like we have a discrete time dynamical system with a stable matrix here, if you like. This is just a number, okay? So if we apply recursively this inequality, what we get is that the optimality gap at any iteration k is smaller than or equal to c to the power k times the initial gap. So the interesting thing is now that the convergence happens at an exponential, or better, at a geometric rate. Okay? So convergence now happens at geometric rate. So if we turn around this bound again, we put some desired accuracy epsilon prime on this gap here, we can obtain the number of iterations that are required to obtain that. And this number of iterations, as you can see, depends now on the log of 1 over epsilon prime, which is the precision. Okay? Of course, then we have to maybe estimate this constant c. If c is very, very close to 1, well, we still have geometric convergence, but it can be slow anyway. If c is small, significantly smaller than 1, then we have fast convergence. Okay, so I don't think, because I want to talk about another thing here. So I think that it's maybe enough for here. I will give you these slides, so you just have some explicit conditions on that you can use as stopping criteria. In this case, either on the optimality gap or of the objective function, or the optimality of the actual optimal solution of the problem. So you can read it yourself. I just want to conclude this part by a couple of examples. So this is a very simple example that you may try yourself. Of course, it's a kind of stupid one because we are trying to minimize a convex quadratic form. Okay, so why is it stupid to apply a gradient method to minimize a convex quadratic form? Well, because in general, the convex quadratic form it's minimized at 0. Okay? But anyway, we want to just to make an example. So the gradient is this is the matrix of the quadratic form is hx. The descent direction is minus the gradient, so it's minus hx. So the iterates of the gradient method are of this form. This is the form of the iterates. And actually, in this particular case, we can write our function phi. And if we look at phi, it has exactly this form here. There's one half. It's a quadratic equation in S, of course. So this is just the line search equation. It's a parabola, and therefore we can solve we can use exact line search here because the minimum step size here is obtained by minimizing that parabola. Okay, it's just the vertex of the parabola, and it turns out that it is given by this expression here. So we can find explicitly the minimum. So the minimum step size, and we can use exact line search. And for instance, this is a two-dimensional example. If we take a diagonal matrix, 1 and gamma, with gamma equal to 5, and we start from some initial point which is also 1 gamma, well, we can see a typical, what can be a typical behavior of a gradient method, which is not very great because sometimes it can, zigzag, do many iterations, zigzagging iterations. In this case, we converge in 40 iterations to a situation where the gradient is less than 10 to the minus 6. And the point here is that the number of iterations that we need will be strongly dependent on conditions. So for this initial condition, if I give this as initial point, I take 40 iterations. If I give another initial condition, so this one here, then convergence is much faster in 10 iterations, and without too much zigzagging, I'm converging to the optimal point. So just to highlight the fact that there could be this issue in the pure gradient method. And also this example taken from lecture notes of Lieven course at UCLA shows just what happens if I try to apply a gradient method where I should not. To a function that can be non-differentiable at some points. Okay? So this function here, it's some function defined in this region to be this square root of something, and to be this other linear function in the case where an absolute value of x2 is greater than x1. So this is not, it's a non-differentiable function, and the gradient is defined only when the absolute value of x2 is different from x1. Okay? And this is the gradient. So the gradient has the following form when x2 is smaller than x1, and when x2 is greater than x1, and when these two are equal, there is no gradient. There will be sub-gradients, but okay. And actually, if we start, suppose that we start at a point in this region, okay, you can check by yourself that actually the gradient algorithm always remains in that region. So we can use this gradient, this expression of the gradient. We can find the step sizes, the optimal step sizes. If we start, so from this point, gamma 1, which is somewhere in here, then you can check that the algorithm converges to 0. Okay? But unfortunately, 0 is not optimal for that function. So we converge to a point. So algorithm converges, but it does not converge to the optimum. Okay? So here is the brief summary of this method. Well, the iterations are generally computationally inexpensive because we only need to evaluate the gradient and do some function evaluation for the backtracking. We do not need second derivatives, so building a Hessian matrix like we need in other type of methods, like Newton method or interior point, well, no, Newton method for unconstrained minimization. But of course it also has some disadvantages, like the convergence may be slow, and of course it does not work on non-differentiable problems. Okay, so you need to make sure that the objective that you are minimizing is really differentiable at all points in the domain. So that's all about what I wanted to say about the gradient method. So I have maybe half an hour or something like that. So I will briefly talk about another related but not strictly related idea of coordinate minimization methods. So what are coordinate minimization methods? So these are methods that apply to functions where each variable or block of variable in the function is independently constrained, or if you like, where no constraints are present, in so-called separable functions. So what we consider is a problem like this, where we minimize some function f0 of a number of variables, x1, x new, these are the variables, and each of the variables is constrained in its own set, okay, in its own set. So there is no coupling in the constraints between the variable. So like I am my variable x1, I live in my little place, and variable x2 lives in its place, but these two places are independent. There is no cross coupling between the variables due to constraints. So the idea of this so-called coordinate descent or coordinate minimization methods is to take this function, fix all variable except one, and then do minimization over that variable, or let's say that coordinate. Then we update the solution, we pass to another variable, and we minimize over that variable iteratively. Okay, so we iteratively minimize with respect to one variable, or can also be a block of variables, with all the other blocks being fixed. So if xk denotes the value of the decision variable as some iteration k, we solve a partial minimization problem of this form. So we minimize over variable xi, because see, all the other variable blocks here are fixed to their previous value at the previous iteration, and we just do the optimization over this single variable or this single block of variables. But this generates a whole family of methodologies based on how exactly we form the next iterate. So there are basically a couple of philosophies, which I think one is called Jacobi method, I think. So in the Jacobi method, we work in fully parallel. In this sense, like we have the values of the variables at a certain iteration, then it is like we have a certain number of workers, parallel workers, that each of them does the minimization over one single block of variables, and then they return their their coordinate solution to the master, who updates the solution. So the idea is the following: the ith block at the new iteration is given by minimizing over the ith block with all the other variables being fixed to the values of the previous iteration. So it's a fully parallel, in some sense, update on the variables. Okay? Well, the problem with this Jacobi type of approach is that in general, of course we can do it, but then we should ask ourselves, are we converging to some minimum or to something? Well, convergence is not guaranteed, even if the function that we are minimizing here is convex and smooth, so differentiable. So in general, these kind of parallel approaches, they do not converge unless we do some trickery. Other techniques are so-called Gauss-Seidel type, or more simply sequential update methods. So the sequential update method is depicted in this figure here. So in the sequential update, okay, I start with some initial value of my solution, of my string of variables. Then I minimize over the first variable and I update the solution. Then I minimize over the second variable and I update the solution. Then I minimize over the third variable and I update the solution, and so on until I swept over all the variables, and then I may start again. So one way of doing this is by successive sweeps over the variables. So you see the difference between this method and the previous one. Here the solution is updated as soon as I finish my minimization on the coordinate. In the previous case, I just have the initial solution, then I minimize over the coordinate, and then I update the solution. Okay? So this is serial in some sense, and the previous one is a parallel method. There is one advantage in doing this thing sequentially, is that at least if the function that I'm minimizing is convex and continuously differentiable, so it is smooth, there is a gradient that I can compute on the function. Actually, if I require that f0 is strictly convex in one variable when the other variables are fixed, then this sequence generated by this serial method of coordinate minimization in some sense converge to an optimal point of the problem. So at least what we can say in this way is there is some form of convergence of the solution in the case of convexity hypothesis on f0. But the point is that it turns out that the area where these coordinate descent minimization methods are useful nowadays deals with functions that are non-smooth, so non-differentiable. Okay, so we cannot use the previous convergence result here because this result here requires differentiability. So actually this method may fail to converge in general for non-smooth objectives even under convexity assumption. Okay? However, there is an interesting and important special case in which we do conclude convergence of these methods, and this exception arises when our function is a so-called composite function, which can be written as the sum of a convex and differentiable function phi and a separable convex but possibly non-smooth term. In simple words, we can apply this sequential minimization method over coordinates to functions that are of this form. So they have one term here, it's convex and differentiable, plus a sum of terms, psi, which are convex but may not be differentiable. Okay? So phi has to be convex and differentiable, and the psi, they just need to be convex, not need to be differentiable. And so why is this special case interesting? Well, you can check by yourself that, for instance, an objective value such as the one that we have in the lasso, this is actually one of the main areas where people may be interested in coordinate descent minimization, is exactly of this form, because in the lasso objective is we have the norm of ax minus y 2 squared plus some parameter lambda times the L1 norm of x, right? This is the lasso. And so this is function phi of x, which is smooth, convex, so convex and differentiable. And this is summation from 1 to n of lambda times the absolute value of x and xi, sorry, and this is my function ci of xi. All right? So this term is indeed convex, separable because we have this summation here, but non-smooth because we saw yesterday that the absolute value function, the L1 norm, is non-differentiable. Okay, and we also computed yesterday subgradients and subdifferentials of that function. All right, so this is a very important special case where we okay, so now under some technical conditions that you may read yourself, the essential point is that when our objective function has this special smooth plus separable and convex structure, then the sequence generated by this sequential coordinate descent method converges to an optimal solution of the problem. So why is it so? Let me give a brief explanation of the reason why that may happen. So for a function, of course we have a standard definition of what is a minimum point, a global minimum point for a function. But we can write things in this way. We can say that z is a minimum point of f whenever f z plus w is greater than or equal to fz for all w. Okay, this is one possible definition of a global and constrained minimum. It means that essentially for all other points different from z, we get something which is no better than f of z. So this is the definition of a minimum point of f. And here we have the definition of what we call the coordinate-wise minimum point. What is a coordinate-wise minimum point? Well, a point is coordinate-wise minimum if something similar to this holds, so f of z plus something is greater than or equal to fz for all xi, but now we are perturbing z only over the ith block of coordinates or over the ith coordinate. So this means that along z is a coordinate-wise minimum point when along any coordinate it's a minimum point. So I cannot find any better point moving along coordinates. Alright? So these two concepts are in general not the same concept. So of course, while it is true that if a point is a minimum point, then it is also a coordinate-wise minimum point, the converse is not always true. So if we have a point which is a coordinate-wise minimum point, so you cannot improve this point by moving along coordinates, that does not necessarily mean that it is also a globally minimum point, okay? So these are these two concepts. For a convex function, we know that a characterization of a minimum point is also this one. So the directional derivative along any direction is greater than or equal to 0. Why? Well, it's intuitively the reason is the following one. So the directional derivative, if we are at a point z, so z is a point, the directional derivative gives us the rate of increase or decrease of the function along a direction. So we have z and we have a direction v, and if we look at the directional derivative of f at point z along the direction v, it tells us if our function is increasing or decreasing along that direction. So if the directional derivative is greater than or equal to 0, it means that for sure the function is not decreasing in that direction. Okay? And if it is so for all directions, anyway I choose v, then it means that we are actually at the minimum point, because any direction I choose and then I move in that direction, then I will not decrease my function. So I am at a minimum. So this is an equivalent characterization of a minimum for a convex function. It means that there is no direction I can move along which I can decrease my objective. Okay? Of course, a point is instead a coordinate-wise minimum point if the same kind of idea. So minimum point means that there is no direction where I can move and I can decrease my objective, and coordinate-wise minimum point means that I cannot improve my objective along the coordinate axis. Okay? In some sense. This is slightly more general because I'm allowing for blocks of coordinates, but it's really irrelevant. Okay. So we have this point here that we already discussed. We can have a minimum point. Any minimum point is also coordinate-wise minimum point, but not vice versa. And so the interesting thing is that we now prove is that if our function actually takes this special form that we already discussed, so convex differentiable plus convex and separable, but possibly non-differentiable, then this proposition holds. So if our function has that property, then any coordinate-wise minimum point is also a minimum point. So we have equivalence in the two directions. So let me briefly explain why. So suppose that z is a coordinate-wise minimum point, then by the previous definition we have the directional derivative along the coordinate axis, which is this, is always non-negative. So we take the directional derivative. Let's look at the directional derivative along any direction now. So this is given by the gradient multiplied by the direction. This is the directional derivative of the differentiable part of the function. Okay? For if we have a gradient of the function, then directional derivative is just the inner product of the gradient times the direction. So since the first part of the function here, we are taking a function which is like this, right? So f of x is given by, I think I call it f0, right? f0, which is the differentiable part plus the summation of the possibly non-differentiable parts. So this is so if we take the directional derivative of f prime is zv, we have a summation, so we have to take the directional derivative of f0, and this is just the gradient of f0 in z times v, so the inner product, plus here we have the summation of the directional derivatives of those other terms. So the directional derivatives of this, right? Which are here. So here are the directional derivatives. So we write this as a summation. We extend the summation here. This is the ith component of the gradient multiplied by vi, which is the ith block in the direction v. So we have this expression here. And what we have here, this is just the summation of I of the directional derivative of f along the coordinate axis. So by our hypothesis, this directional derivative is greater than or equal to 0, and then we conclude that the directional derivative of the odd function is also greater than or equal to 0 along any direction. Okay? So this permits to conclude that z is also a minimum point of f. Okay? So we prove this proposition. If a point is a coordinate-wise minimum point, it's also a minimum point under the assumption that the function has that structure. All right, so this is more or less this is the sketch of proof now of the fact that due to this equivalence between minimum and coordinate-wise minimum point, well, we can see that sequential method of updating the variables, it's not difficult to understand that it converges to a coordinate-wise minimum point. At a certain point, if we minimize over the coordinate direction, there is a point in which we finished, and any direction we look at, there is nothing to minimize anymore. So we converge to a coordinate-wise minimum point, and then we appeal to that result, and we conclude that if f has this structure, we actually found a minimum point of our function. So I don't want to go to the details, but I want to leave you a little exercise if you like. So the exercise is just to apply this idea to this problem, to the lasso. So you can go to MATLAB and code in MATLAB your coordinate minimization algorithm for solving the lasso. So basically, you should write a function that you are given matrix A and vector y and some parameter lambda, which is the trade-off parameter here. So lambda is some number greater than or equal to 0, and then you should write your coordinate minimization method for the lasso. Okay, here is some hint, because it's not simple as it seems. There is one important aspect. Why should we use coordinate minimization? Well, we may be interested in using coordinate minimization when the problem that we need to solve over one coordinate is very simple. Okay? If the single variable or single block minimization problem is easy to solve, or even we have a closed form solution for that, then it may become interesting to use the coordinate minimization scheme, because each sub-problem we are unpacking the problem into a sequence of sub-problems over the coordinates. And if each sub-problem over coordinate is very, very simple, then it can be effective. So the point is, you have to check what happens when you reduce you take the lasso problem, you fix all variables. So suppose that all variables are fixed except one, okay? Except the ith variable, okay? And then you obtain a problem over only one coordinate, on a scalar variable. And the problem over a scalar variable from the lasso looks like this, okay? You have to minimize over only one coordinate, so it's over a single real variable, a function like this. So it looks innocent, but it takes a while, if you haven't seen it before, now to understand how to find an optimal solution for this problem in closed form. Okay? To make things simple, I give you the optimal solution for the univariate optimization problem, but I ask you to think of how you come up with that solution. Okay? So the solution over the coordinate, the optimal coordinate of the subproblem is given by this formula here, which by the way is known as soft thresholding function. So basically, finding the minimum over one coordinate is very easy, is in closed form. Okay? Then you have to go sweeping over all the variables until you converge.
But for this example, I mean lasso, concrete example, there is no problem to calculate it explicitly Rock's mapping, that is the linearized quadratic form, and it is shrinkage mapping, and it can be done in explicit form.
Yeah, sure, but the problem is that yesterday lecture I should have talked about proximal methods, but I didn't, so I don't know if the audience here knows what is the proximal mapping.
We know a lot.
Okay, everybody knows about the proximal mapping. Okay. Anyway, yeah, of course, there are other methods, of course, for solving the lasso, and one of them is to use a proximal gradient method, right? Which gives you something else, but I didn't talk about proximal methods. So this is just coordinate descent method, and it turns out that you also need to use this soft thresholding function. All right, so you can use this in your solution of the lasso. Okay, I think I'm finished in time, so I thank you everybody.
I have a question. Yeah, the way you presented the Gauss-Seidel and also the Kobe are centralized arguments. There are distributed versions.
No. So this is just the ideal scheme in which you solve the problem. In the Jacobi method, actually is not centralized, it is completely parallel. It's completely parallel. It means that if you want to see things that way, a Jacobi method can be fully parallelized. So you have workers, this is the picture exactly. So you pass, a master passes the sub-problems to a lot of different workers. Each one independently solves the problem and then brings back the solution to the master. So this is fully parallel. Instead, these other sequential, this is not, because this, for instance, the second worker has to wait for the first worker to finish his minimization before it can proceed.
Yeah, but there are versions of Gauss-Seidel which can be parallelized.
But not this one.
Not this one.
Not this
but
one.
I'm thinking about the book by Gatsekas and
Yeah.
there are lots of versions.
Not in this pure sequential form.
Because of course you're right.
I have to wait.
But there are other versions of Gauss-Seidel.
Yeah. Gauss-Seidel is like a general term that describes a lot of different things. So, Okay.
Other questions, please? No questions, okay. It was a